Towards the end of my previous lecture, I described the problems associated with the Aristotelian universe. The Aristotelian universe cannot explain the following observational facts. Number one, Mercury and Venus are never visible in the middle of the night. They are only visible during twilight hours. And then secondly, retrograde motion. Specifically, I cited the example of Mars. The ancient Greeks basically chose to ignore those problems associated with their model of the universe, hoped that they would go away. Well, those problems did not go away. And then we once again get to the Roman astronomer Ptolemy. Okay, I previously have described how Ptolemy is known for measuring accurately the distance from the Earth to the Moon. That distance is 60 Earth radii, but he's also well known for the following idea. Ptolemy comes up with a mathematical scheme, if you will, more or less an ad hoc explanation of how you could still keep the Earth at the center of the universe and explain away the problems associated with the ancient Greek model of astronomy in failing to explain those observational facts. Ptolemy's idea is a little strange. It's called Epicycle theory. So Ptolemy devises epicycle theory. It's a mathematical scheme to explain away the problems associated with the planets and still keep the Earth at the center of the universe. The problems associated with the planets and still keep Earth at the center of the universe. Okay, Ptolemy's model goes in the following manner. Okay, so first of all, we have here the Earth like so, still at the center of the universe. And then we have this large circle that Mars is moving upon as it moves around the Earth. Ptolemy gives this circle a name. He refers to it as the deferent. However, in addition to moving on the deferent, Ptolemy also assumes that the planet, we'll use Mars as an example, the planet Mars also moves on another little circle that is centered on the deferent, and this is called the epicycle. That looks like this, like so. And then right here we'll say is the planet Mars, for example. This little circle here is the epicycle. So you have the planet Mars then rotating around this epicycle like so, while the entire time the planet itself then, the epicycle that is, moves around the Earth. So you combine together two types of circular motion. If you combine those two types of circular motion, you then end up with basically the following path. All right, so combine two types of circular motion. And you then arrive at the following. Basically something that looks like this. Or right here, for example, is the Earth. Okay, now go ahead and pause this lecture here at this point. And then what I want you to do is I want you to watch the screencast that I've posted for you called Retrograde Motion Geocentric Model. Go ahead and watch that screencast now. Okay, now that you've watched that screencast, you can then see from that screencast the two types of circular motion that give rise then to this idea. Now, if you fudge around mathematically with the size of the epicycle, how long it takes the planet to move around the epicycle, you could actually get this mathematical scheme to fit the appearances that we see in the sky for all the planets. You could also get it to explain away the problem associated with Mercury and Venus not being visible in the middle of the night if you appropriately address the mathematics of the epicycle itself in the case of those two planets. So as strange as the idea sounds, you can actually get it to work. Okay, now kind of moving forward in history from this point. If you're familiar with your basic European history, soon after the time of Ptolemy, he lived around the 1st and 2nd century AD. Soon after his lifetime, basically the Roman Empire collapsed. When the Roman Empire collapsed, what is referred to as the Dark Ages ensued in Europe. With respect to astronomy, no further progress was made in Europe over an extremely long stretch of time, a stretch of time of about 1400 years. During this extremely long stretch of time, if you wanted to learn anything at all about astronomy in Europe, you went to always the exact same source. Another reason that we remember Ptolemy today, by the way, is that he's actually our primary resource, if you will, historically, for the ancient Greek astronomy that preceded him and also his own work. He combined all the ancient Greek astronomy that preceded him and his own work into a single volume. That volume has an Arabic name. It's called the Alma Guest. The Alma Guest is a compilation of Ptolemy's work and the ancient Greek astronomy that preceded him. Think of it, for example, as a textbook. And then over 1400 years or so of European history, if you were a European and you wanted to learn about astronomy, you went to the Alma Guest because that was basically the only source that was available to you. Now, through trade, however, over the centuries, other cultures, primarily Arabic, Hindu, and Persian, those cultures became aware of Ptolemy's work. They became aware of epicycle theory. And then mathematicians in those cultures expanded upon Ptolemy's work. In order to make better and better measurements of planetary positions in the sky that ensued over the centuries fit Ptolemy's model had to become mathematically more complicated. In other words, over the years, over the centuries, our abilities to measure planetary positions in the sky got better and better. They got more and more accurate. So to account for all of this accuracy, mathematicians in those cultures had to do all sorts of weird, torturous things mathematically to Ptolemy's model to still get the idea of epicycles to fit what we see in the sky. They would have to literally do things, for example, like say piling epicycles on top of epicycles. Now, why would all of these mathematicians in all of these different cultures spend all of this time and effort trying to explain planetary motion by using Ptolemy's scheme of epicycles? They did so for astrological reasons. In other words, what they were trying to do was cast accurate horoscopes. You have to remember that to the ancients, there really was no difference between what we think of today as the natural science of astronomy and the superstition of astrology. They were all very much wrapped up together as the same thing. So all of this effort was basically being done for astrological reasons. This is the only contribution that astrology has ever made to anything. Astrology basically kept this process alive over the centuries, and it's the only contribution that it has ever made. Let me briefly summarize that here. Okay, so after the Roman Empire collapsed, through trade, other cultures became aware of Ptolemy's Epicycles. And then over the centuries, as measurements of planetary positions improved, by the way, you measure planetary positions by basically measuring angles on the sky, using versions, for example, of protractors. But over the centuries, as measurements of planetary positions improved, mathematicians had to make Ptolemies Epicycles increasingly more complicated in order to fit the appearances. In other words, still use epicycles to explain what we see in the sky. They would have to, for example, pile epicycles upon epicycles in order to do so. So let's say, for example, that right here is the deferent from earlier. Here's the Earth like so. Here's the epicycle for Mars, for example, that I described earlier. And then right here is yet another epicycle. And then yet another epicycle on top of that. So mathematicians had to make the model increasingly more and more cumbersome in order to explain what we see in the sky. Basically, while all of this was happening over the course of centuries, literally nothing happened in Europe for about 1400 years. Once again, all of this was motivated by astrology. This is astrology's only contribution to anything. As I said, during this time, basically nothing happened in Europe, no further progress was made. However, I do want to mention the following, which did occur in about the 13th century or so. In the 13th century, there lived a man named St. Thomas Aquinas. He was a Catholic theologian. He was not an astronomer. He was not a mathematician. However, basically what Aquinas does is he incorporates the Aristotelian universe into Catholic theology. He basically makes it part of the religion. So, for example, Aquinas looks at the idea of an Earth-centered universe and he really likes what he sees. So in his own mind, mankind is God's most perfect creation, so then therefore we should be at the center of the universe. And then like the ancient Greeks that preceded him, for whatever reason, Aquinas latches onto this idea psychologically that all motion in the heavens has to be perfectly circular. Once again, this idea of a circular geometry represents some sort of perfection. So then therefore, because the heavens are perfect, this then means that all motion in the heavens has to be perfect. So basically what Aquinas does is he takes ideas that predate Christianity by several centuries and he basically incorporates it into Catholic theology. So then therefore, if you come along and you're living in medieval Europe and you look at Ptolemy's model of increasingly more and more complicated epicycles, and you say to yourself, this can't possibly be correct, there has to be a simpler explanation to describe planetary motion. If you're in Europe at the time and you say that, you are basically challenging the political authority of the church. You are committing heresy. And because the Catholic Church was the dominant political power at the time in medieval Europe, if you committed heresy, basically two things happened to you. Number one, you were excommunicated, which means that you were thrown out of the church. But then perhaps more importantly, number two, you were executed. And it wasn't an idle threat. The Catholic Church, for example, was executing heretics for as late as 1600. So then therefore in medieval Europe, it was basically you wanted to keep your head down, more or less, if you will, if you come along and you challenge the idea of the geocentric universe. Let me go ahead and pause here for part 2 of this lecture.